So let's try and connect the electrochemical dots. So what do I mean by that? So how do we relate E and delta G and K? All right, so from physics, we can go ahead and we can kind of borrow some ideas. So the electrical free energy, it's going to have units of joules, and it turns out that it's going to be equal to the charge on an object multiplied by the potential difference over which it moves. And the potential difference, we often refer to that as the voltage. And the charge, we normally measure in coulombs. So I should probably define what I'm writing down here. So this is the charge measured in coulombs. Okay, and this is the potential difference measured in voltage, or volts. And this, of course, is our friend, the joule. So electrical free energy, well, I can write that as work is equal to charge times by electrical potential difference. I can use symbols or I can use the units however I want to. So we would really like to know, how do we figure out the charge on an electron? And you might say, oh, come on, dummy. An electron's got a negative charge, right? It's -1, but it's not. So it's -1 times by a constant. So we have neglected that bit of information probably for a very long time, and now it's time to rectify it. So there was a very famous electrochemist called Michael Faraday. And Michael Faraday was the first person to really measure the charge on an electron. In fact, he measured the fact that, this is in the 1800s, by the way, he measured that 1 mole of electrons has a charge of 96,500 coulombs. In fact, it actually has a charge of minus 96,500 coulombs. So you can use that, and of course you could divide by 1 mole to get the charge on a single electron as well. Now, we refer to this in his honor as the Faraday. So we go ahead and we define 1 Faraday as being equal to 96,500 coulombs per mole. And the way to think about it is that if you've got 1 mole of protons, it has a charge of 1 Faraday. And if you've got 1 mole of electrons, it has a charge of -1 Faraday. So that's the connection that we're going to need here. We can also see that the volt must have units of joules per coulomb, because if you multiply coulombs by something and you get joules, then that something must have units of joules per coulomb. So the volt actually also can be written as 1 joule per coulomb. In fact, this kind of kicks back to something that we mentioned earlier. The voltage is the electrical kick, the energy that we give to the electrons as they move from one side of the cell to the other. So it makes sense it would have units of joules per charge, so joules per a certain number of electrons. Okay, so if we go back to that initial equation, right, so that work, that free energy is equal to charge times by potential difference. We can see that the work here is going to be delta G. We said earlier that delta G is the maximum work a system can do. The charge, okay, so how would we do that? So we know that Faraday's constant is the charge on 1 mole of electrons. And we know that we can use N for the number of moles. So if we multiply N by F, that's the charge on a mole of electrons. Actually, it's not, is it? Because electrons have a negative charge. That would be the charge on a mole of protons. And we're not moving protons around, we're moving electrons. So hence we should write that as -NF. The potential difference, right, that is just the cell voltage. And so we can put this all together, and this is one of those sort of famous equations that I think if you're going to get a tattoo, that's probably one of the top 10 chemical equations to write. And that connects the world of electrochemistry with the world of thermodynamics. So very, very cool. All right, so if we're under standard conditions, then we can also rewrite that as delta G standard is equal to -NF E cell standard. So that's when we've got all our concentrations at 1 mole per liter, pressures at 1 atmosphere, and solids and liquids are pure. So we can actually put this all together now. In fact, we can go ahead and we can write down our own Rosetta Stone. So we know that E cell standard connects to delta G via this equation. So we can go in one direction or the other. So we can go this way or this way. So for instance, we know that delta G standard is -NFE. Or if we rearrange, we can say that E cell is just equal to minus delta G standard over NF. So we can go between them one way or the other. We can build some other connections too. So we know that delta G standard and the equilibrium constant are connected as well. If you remember from the last chapter, right, we said that delta G standard is equal to minus RT log K. So we can write delta G standard is minus RT log K. And if we want K, we can divide both sides by minus RT and anti-log. So that would give us K is equal to E to the minus delta G standard over RT. And we can do the same kind of thing to relate between K and E cell if we want to. In fact, we can just say, well, if delta G standard is minus RT log K and delta G standard is minus NFE, we can relate them equal to each other. So what does that mean? So that means that minus NFE cell is equal to minus RT natural log K. So we can divide both sides to get E cell. So that's equal to RT over NF times by the natural log of the equilibrium constant. Or we can go ahead and we can get in terms of K. So we can multiply both sides by NF over RT and then anti-log. And that will give us K is equal to E to the power of NF E cell standard over RT. Kind of a mouthful, but now we have that Rosetta Stone. We have that ability to go in between any one of these threes in either direction. So that is why that is amazingly powerful. In fact, if you wanted to build our own Rosetta Stone, right, so it would look something like this. We would say, here's delta G standard, and here is the equilibrium constant, and here is the cell voltage. Okay. And we could go ahead and we can say when delta G standard is negative, that implies the equilibrium constant is greater than 1. And that also implies the cell voltage will be positive. Okay. We can also say that when delta G standard is 0, the equilibrium constant is exactly equal to the number 1. And E cell standard is 0. And our last column, we can say when delta G standard is positive, so that's unfavorable, our equilibrium constant is much smaller than 1, and our cell voltage should be negative. So remember, what does non-spontaneous mean? It means it won't go in the forward direction, instead it goes in the backwards direction. So falling uphill is non-spontaneous, but falling downhill is obviously the spontaneous way. So that is our Rosetta Stone. That's pretty cool.